Hello, Calculus 2 students, and welcome back to Maggie Mathics. In this video, you're going to learn 7 tricks to fit integrals into known integrals. What I mean by that. So all you do in Calculus 2 is take integrals for different purposes, sometimes to calculate area under the curve, sometimes to calculate surface of revolution, volume, center of mass, whatever the case may be. The main thing that you do is take integral. And in the beginning of Calculus 2, you're given these formulas, 20 basic rules of integration. But then you're asked to solve integrals that don't look like that. Actually, rarely you're going to see integrals that look exactly like that. In this video, you're going to learn how to transform integrals into known integrals, because there needs to be usually 1 or 2 algebraic steps done to the integral so that they look exactly like this. And once they do, your job is done. These integrals have been solved. They were solved in 17th century, and we know the formulas. And you're going to just look at the formula and copy the answer, and that's it. As long as you make them look like that, you can be like, I've done it. So that's the hard part. So in this video, you're going to sharpen skills of taking integrals or making them look like takeable integral. So let's get skills. Trick number 1, expand. The reason why is just what we discussed. It doesn't look like any of these basic rules of integration, so you need to do algebra, and the trick here is to expand the expression. In the first case, it's binomial, and in the second case, just multiply it through. Pretty simple. So I'm going to do just that because all the good things happen when you expand the expression with integrals. Dx applies to all of them. Now I'm going to write here, integral of a sum of terms is sum of integrals. Here you have sum of terms. What integral is, the definition of it, it's calculating area under this curve, and this curve. Well, areas of anything, like an area of this square, can be added to its neighbor square linearly. You just add areas. You've always been doing that, and with integrals, areas can be linearly added, and it comes from linearity of integral that you can take integrals of these functions and then add them after you take the integrals. And notice that all the constants are popping out of the integral because the less you have going on in the integral, the better. Right now, all 3 of the integrals are looking like one of the basic rules of integration. U and du. Look for that in your formula sheet and you'll find it. And the formula for that is that u here is x. For some reason, all the formulas you have, instead of x, they use u, right? So that is the formula. You increase the power by 1. So if you have x squared, you increase it by 1, so you'll have 1 more x. And then you write the same exact numbers in the denominator. So if you start with x squared, you end up with x cubed. That is how generous integration is as an operation, as an operator. Different from derivative, which is a diva, and it kills x's. Instead of giving you x, it takes away 1x at a time, right? Here, you have basically 1 times dx, and what you really have is x to the power of 0, because anything to the power of 0 is 1. Okay, so you just treat that the same that you did x squared or x to the power of 1, right? You have x to 0, so you add 1, and you write the same thing in the denominator. And you will end up with x 0 plus 1, that's 1. So that's how you end up with x when you have integral of dx, or 1 times dx, right? So that's the final answer. Oh, well, maybe it would be more polite if you canceled whatever you can So this is the power of this trick, expanding expression that you have in the integral. You always want to have some of terms separate so that you can take these integrals, and that is something that you can always do. By the way, this step, writing 3 separate integrals, is optional, and as you advance, you're not going to do that because you're just going to like kind of do that in your head without writing it down. You'll just, from this step, you'll jump to this step. But in the beginning, write down every step. This second integral, I'm just going to include answer here. You can screenshot it or you can try to pause this video and solve it on your own. All I'm doing here is simple algebra. Multiply through like this, then -5, right? Then combine like terms, and once you have this, then you can have separate integrals, and this is the final answer. In this case, all of them ended up being power rules. So that is the power of expanding, so that you end up with separate integrals. Okay, trick number 2, separate the numerator. Okay, so what you want to do here is separate the numerator, and the reasons for why you want to do that are very much the same reason why you wanted to expand these expressions, so that you would have integral of sum of terms, so you could take separate integrals. Now you're going to separate these so that you can have sum of 2 fractions. Usually what you do is that you have this type of a situation, and as soon as you see the same denominator, oh, I can put these together. So I can say, and there will be 1 fraction. But in this case, you kind of separate them, because with integral, you always want to be able to write separate integrals. So that's what I'm going to do in the next step. And the reason for this is that in the first integral, this one that I'm writing down right now, what we wanted already happened. This is one of the basic rules of integration. If you don't recognize which one, look in your formula sheet. Let me show you. Okay, so we have a variable square plus 1, but that could also be 1 squared, because 1 square is 1. Look here. You have number square plus, but order doesn't matter as long as you have plus sign here, because remember, 5 plus 6 is same as 6 plus 5. So here you have a variable square. Okay, it is arctan, where a is 1, so we won't have 1 over 1 because that's just 1. Arctan of x over 1, but we don't write that, we just write x. So the first one is good to go. This is why we do this trick. We are solving integrals, but really what we're trying to do is we're trying to learn the trick of separating numerator and other tricks in this video, because this is so versatile and universally applicable. You're going to use this trick all the time. When you see a fraction like this, you want it written like that so that you can apply different rules and approach them separately. So the second integral needs a little bit more help, and it needs a u sub. Usually what you want ideally is the entire denominator, usually, to be u. But the question you would ask then is, do I have derivative of the denominator sitting in the numerator? And you do, because derivative of x squared is 2x dx, but I can take care of 2. And derivative of 1 or any constant doesn't worry me, because derivative murders constants. So I'm going to say with confidence that u is x squared plus 1. Now, taking derivative of x squared is 2x. I don't have 2x dx. I have x dx. And I like to do one extra step, which is optional, to express exactly what I do have. And that is simply done by moving this here so you isolate that which you have here so that you substitute this by exactly what it equals to so that you don't accidentally, God forbid, write that x dx equals to du. No, no, no. It equals to du over 2. I'm going to rewrite the first integral without taking it. I'm going to take both of them in the same step. And the second integral I'm going to rewrite as my new rephrased u sub. And notice that 1 over 2 du that I'm going to write here, du over u, right? I can take that 1 over 2, since that is a constant, out of that integral. And I always like to do that. The less I have inside of the integral, the better I feel. All right, notice that this one, oh, dx, no thanks, du. Notice that this integral is one of the basic rules of integration. It's ln. So you will have this integral in your formula sheet that equals 2 plus constant of integration. So both of the integrals are now solvable, integrable. These I can handle. Arc tan x for the first one plus 1 over 2 ln u. Last step left to do, and what I need to do is with indefinite integral, which we have right now, it doesn't have bounds, right? So it's indefinite integral. The answer to this integral would be some function of x. And it should be function of x because the question was posed in terms of x, or it was asked in a language of x. And you can't answer the question in a different language. So we need to go back to the initial variable. And at this point, you don't really think. Anywhere you see u, you replace that with the expression that you promised u would equal to. In this case, x squared plus 1. And now you're done. Box this answer, and let's not lose track that we're not solving, or we are solving integrals, but that's secondary. What we're really doing is appreciating the power of this trick, separate numerator, that you can use to solve so many different integrals than this one throughout your calculus 2. Trick number 3, complete the square. This one is so important. This is what I'm going to work on separately, okay? So right now, I'm doing algebra. Look how much algebra I'm going to do before I do calculus. Just rewrote it. Now I'm going to rearrange. Start with negative. Rearranged it. Now going to take out negative out. And if you're asking, where do I get negative when you have positive? Well, inside of any positive, there's double negative that's sitting there. And if you don't believe me, then you can put this negative back and you will get negative x squared plus 2x, right? Exactly what you started with. So you have done everything right. I'm going to write this as a perfect square, kind of, in that type of a way so that it's easy for me. And here, I'm trying to make it look exactly like somebody's square so that I can think of which number would I add here, and I obviously have to subtract the same number, otherwise I have violated laws of math, right? So that would be 1. Notice here that this is x minus 1 squared. I completed the square. Of course, I need to also subtract 1, but I think I'm on a right track. X minus 1 squared minus 1. Now I'm going to put this minus back here that I took out at this stage on that during that step. Plus 1, right? And I'm going to write that positive first. And I will explain why we did all of this in a second. This expression is the same expression as that expression. It's just same idea expressed in different words. And I did all of this. Let me separate this so that you know. This is just me doing algebra. Welcome to Calc 2, where you realize you have never done so much algebra in your life. Okay, now I'm going to rewrite this integral with this new expression. 1 minus let's get our formula sheet and see. We clearly have this scenario. Now we do, but before we didn't. So this is 1 squared, that would still be 1. Some variable squared minus, some constant a squared minus a variable squared. For us, that's x minus 1 squared. But 1 doesn't have a little variable popped there the way that we started, and that is arcsine x over a, or u over a. So if you're worried that this does not equal to, x, there's some expression x minus 1, well, think of derivative of x minus 1. It's just 1, right? Because derivative of x is 1, and derivative of negative 1, or any number, constant, is 0, because derivative merges numbers. So if derivative of x minus 1 is 1, that means that du will be dx. So u substitution is optional, but I've talked about it so much, might as well do it so that we take everything slowly. Okay, so u is x minus 1, du is dx, or 1 times dx. Okay, I can rewrite this integral. Now it's going to look exactly like the basic rule of integration, which is the whole purpose of this video. This is the difficult part in calculus, to make the integrals that you're presented with look like one of those basic rules of integration. So now it looks exactly like arcsine, right? So I'm going to say arcsine u over a, but that's 1 for us. And let's actually write here that a is 1. And constant of integration. Of course, nobody asked me a question in terms of u. They asked me in terms of x. So I'm going to back substitute with the expression I promised u would equal to. By the way, arcsine and sine is the same exact thing. It's just 2 different notations. So don't let that confuse you. Rule number 4, divide improper function. These are one of my favorite integrals because it's so confusing. You can do anything to these integrals and you can't solve them until you make them proper. And what makes a function improper or rude? Remember it like this: rude or improper function is the one that presented to you like these. Like this is another, these are improper as well, but these are examples that we can discuss so I can explain what an improper function is. Improper function is the one that order of polynomial which is 6th here, the highest power of x determines the order of that polynomial. So in this case, there are no other, but if there was x5 here, it would be 6th order polynomial. When the order of polynomial in the denominator is higher than order of polynomial in the denominator, higher or equal to. This is also rude and improper, okay? Neither of these are right. And you can remember it like this. So there's higher number in the numerator than in the denominator. And it's same as or similar to if you asked me a question, how many siblings I have, and I told you 24 over 12 instead of telling you 2. Well, it is 24 over 12 is 2, but it's not the smallest ratio, so I told you something weird, right? So you have to divide it in your head. So here, this is not the smallest ratio, so they didn't finish the job. They gave it to you so that you finish it. So this is not a function that you can take an integral of. This is improper function. So you need to divide this function by this function. Like if I told you 24 over 12, you would have to divide this by this number, right? So we're going to do just that. And I have 2 examples here. I'm going to solve both of them carefully because I doubt if you remember the rule for doing long division. And you can divide functions using long division or synthetic division. I'm going to do long division. So the most important thing here is that whatever is in the top, in the denominator, goes in the right-hand side. And whatever is in the denominator goes in the left-hand side, okay? Now you ask the most important question. What do you need to multiply this term by so that it looks exactly like this term? Well, x needs another x and number 2 to be 2x squared. Well, that's your answer. 2x. So now you multiply 2x by x and by negative 2. And you write it in this line. Then I like to do an extra step. This is optional, but this I have to subtract vertically, right? So I have to say 2x squared minus 2x squared minus 3x minus 2x. And I don't like to do that. I like to vertically add instead of subtract. So I'm going to change the sign of this line and multiply it by -1, right? So each term I'm going to multiply by -1 so that I can add vertically rather than subtract. But cross this one out so that you don't accidentally add that line. You don't need that line anymore. So now I vertically add, this is 0, which is why I did that, right? Minus x plus 1, because this gets transferred here because there's 0 here. Okay, now you ask the same question. What do I need to multiply x by so that it looks exactly like this? It's almost there. It just needs -1. So -1. Now you multiply -1 by x, -1 by -1, plus 1. And I'm also going to change the sign of this line as well. Don't forget to cross it out because you don't need that anymore. I'm out of room. So this will be -x plus x, 0, +1, -1, 0. Oh, couldn't help that. So what just happened? You divide this function by this function and you get this answer and 0. That means that we evenly divided it. We were able to evenly divide. It's similar situation to 24 over 12 instead of 24 over 13, right? There you would have a remainder. Here you don't have. It's 0. So all you ended up with is 2x minus 1 dx. That was my side work. This is me doing calculus here. Now I'm going, dx applies to both of them. Now I'm going to separate these integrals and take two integrals. 2 comes out of the integral because I don't like to have extra things in the integral. Oh, I can take both of these integrals. Both of them are power rule, right? So 2x squared over 2. Integration is a generous operator. It gives you additional x back. So these get canceled. And that's your final answer. Let's appreciate the trick here. Divide improper function. You couldn't take this integral without dividing this improper function, and always pay attention to this. Don't jump into the problem. First see that if there's higher number here as the power of x than in the denominator, then that integral needs help, that function needs help. I'm going to divide this function as well. Again, because it's probably been a while since you have done long divisions. You were probably hoping you would never again have to do it. You're too advanced for this, but here you are. To the right goes numerator, and to the left denominator. You ask the question, what do I need to multiply this by for it to look exactly like that? Well, it's already there. So 1. X squared plus 1, multiply both of that by 1. Change signs. Cross this out. 0 and minus 1. Now you ask the same question. What do I need to multiply this by to get it to look exactly like this? There's not a single number that you can multiply x squared by so that it is -1. You can divide it, but that's not what we're doing here. That's not the question. What do you need to multiply it by? So nothing. And that means that you're done. That is the remainder. We were not able to divide this evenly, but that's okay, because some numbers like 24 over 13 don't divide evenly. But I have 1 from here plus whatever the remainder is over what I wasn't able to divide this by this evenly. So you write it like that, like a fraction, because you weren't able to finish the job. Okay. So do you see how you have terms being added? So I'm going to take separate integrals, and this minus here will come here, right? So I'm going to have integral dx. The first integral is power rule. It's x. There's x to the power of 0 or 1 sitting there. So that's x. Oh, minus. Minus, and this integral, we already had this integral already at trick number 2. Yeah, here. This integral is arctan x. You can also look in your formula sheet and see what that is. X minus arctan x plus constant of integration. There was no u sub, so we are done. Okay, that's the final answer. Let's see what we did. Divide improper function. Improper because the order of a polynomial in the numerator as well as denominator was 2. So we needed to fix that because it was improper. So these are improper because, again, higher number, lower number in the denominator. It can be divided. You divide it using long division. Now it's looking like one of the basic rules of integration. See how much you have to do to make it look like one of the basic rules of integration? Trick number 5. Create terms in the numerator. Okay, this trick is used, obviously all of these tricks are going to be used in so many other integrals than examples I have provided, but there's this one very interesting integral, which I have a separate video on. I will include it here. It should say here, right top corner. So in this integral, you have to add terms. And in this case, you add ex and you subtract the same thing. Obviously, in our example, we're not going to add that because you need to add something that makes sense. You can't just add the same thing each time, right? And how do you determine what you need to add? And here goes the thinking. I'm going to think out loud so that you know how you decide that, because that's important. Because, okay, you can recognize that you need to add something, but what do you add? And this is how you arrive at that. Okay, so this I noticed was somebody's perfect square, and that is x plus 1. I was like, surely they want me to rewrite this. They gave me a perfect square. They want me to rewrite this as x plus 1 squared. Then I have this to add x here. And the problem with this integral is that it doesn't look like any of the integrals in your formula sheet. So you can't have this equal to u because you have x here. If you didn't have x there, then yeah, you could do it, because then it would be, this would be u, and then it would just be 1 over u squared. But you have x here. That's what's complicating things. So my thinking goes like this. It would be nice to have x plus 1 here. Then I would cancel this with that. And I would have x plus 1 to the first power here. And then just 2. No more x there. That would be nice to have. I don't have that, but maybe I can have it. So I can add something here. And of course, I'm going to subtract it as well. So I bring out 2, and I'm left with x plus 1. Okay, then if I put 2 back, x will have 2, and this will be 2. Okay, then I need to add 2. And I need to subtract 2. Okay, and in the next step, I'm going to bring 2 out. I'm going to have x plus 1. I still have minus 2. All of that over squared. Now I'm going to use, I told you that these tricks are extremely versatile and universal in application. You're going to use them all the time. Remember trick number 2, separate numerator so that you have 2 fractions added. Okay, I'm going to do that here. I'm going to use trick number 2 in trick number 5. So I'm going to have this integral, and I'm going to have this integral separately added to one another and see what happens. Oh, 2 from the first integral comes out of the integrand because that's a constant, and I can do that. X plus 1. Now that there's negative 2 here, I'm going to bring that out as well. Dx x plus 1. You're probably saying, oh my goodness, it still doesn't look like any of the basic rules of integration. Well, it will very, very soon. Okay? You didn't have to do that. You could say that x plus 1 squared equals to u, and then your du would be that. But I'm going to cancel it because I think that's the most obvious and the simplest, and I'm going to do that. And now I'm going to do u sub. These 2 integrals are separate integrals. They need to be respected as separate, sovereign, independent integrals. But it so happens that u for both of these integrals is going to be the same thing, which is x plus 1. So I'm going to do 1 u sub. And if u is the same thing, then du has no choice but to be same as well, because du is derivative of x plus 1, and that is 1. And in this case, u sub is optional, but I'm going to do it. Rewrite this to integral of du over u minus 2 integral of du over u squared. Don't forget that you have square here and this square was canceled. Okay, now both of these are basic rules of integration. 2 ln u for the first one. And the second one is, if you don't see which rule that is at this stage, then you can write it as u to the negative 2. You can bring this upstairs, and when you or anybody is in the basement, fun things happen in the basement. Games, snacks. If you're made to come upstairs, you come upstairs with a negative attitude. So u comes upstairs with negative power. Then you can treat this as it's simply n. So you increase. So this is you increase by 1. And you write the same exact number in the denominator. So u, negative 2 plus 1, negative 2 plus 1, plus constant of integration. Now, obviously, this expression looks a little bit intense and you need to kind of civilize the answer. Oh, and also you need to put back the variable that you were asked the question in, which is x. You can't answer the question in a different language than the question was asked in. It's simply rude. 2, and this is u to the power of minus 1. It wants to go to the basement, so it has better attitude, so I'm going to put it there. And it's divided by negative 1. So this will turn positive, and u goes in the basement, and instead of u, I have x plus 1, right? So that you go back and back substitute. This is the final answer. That was trick number 5, create terms. And as I told you, in this case, this integral would not get solved. And you also, in this integral, how do you know what to add? Here you added something totally different, which usually would be the case. You can't add the same thing, right? You start solving it and you start thinking, what would be nice to have? Oh, if I had this, then I could solve it. And then you give yourself that term. And don't forget to also subtract, otherwise it would be like mathematically illegal, right? And then we did step number 2 within step number 5, or trick number 5, and that was funny. And then we canceled those, and then it still didn't look like basic rules, but after we did this u sub for both of them, and the u was same for both, then they looked like basic rules of integration. Okay, trick number 6, you almost made it, you have 2 more to go. So here, step number 6 is use trigonometric identities. Then what I mean by that is this relationship, that tangent square x. And by the way, why do I have 2x there instead of regular x so that it would be simple? I don't know. But then I felt bad and I already did u sub for you. So this relationship, it's very much fundamental, and it actually comes from something even more fundamental, which is Pythagorean theorem. And this is the Pythagorean theorem in x and y, but this is Pythagorean theorem in the language of trigonometry, because you assign here, comes from that triangle. And a lot of algebra, and then you can go through the steps. You can take a screenshot there. It's ready for a screenshot for you. It's part of the fundamentals. This is the relationship, okay? And we're going to use that here because we can't take antiderivative or integral, which is antiderivative of tangent square x. And this is just, I guess, makes you practice u sub. Okay, so then instead, I'm going to write tangent square x as what it equals to, which is secant square x minus 1. And I have du here, so I'm going to do, this is 1 over 2, so I'm going to write 1 over 2 here outside of the integral because I don't like to have clutter in the integral, and that is u minus 1 du. Okay, there is an integral of the sum of terms, so I'm going to separate that and have two integrals instead. Something we've been doing all along in this video. Don't forget that this 1/2 applies to both terms, right? Now you can take this integral, because if you look in your formula sheet, you have secant square x or secant square u du. And this one is a simple power rule where there's 1 du, so u to the power of 0. Increase that by 1, so you end up with u when you started with 1, because integration is that generous. Now you need to put back this instead of u, and those 2's will cancel, and you will end up with minus x plus the constant of integration, and that is your final answer. There's another way to solve this. Actually, I just realized that when this 1/2 and 2x canceled, this 2 came from the fact that this was 2x, right? U equals to 2x. If it was 5, it would be 5, and there would be 5 here, and then it would be du over 5. And I would have 1/5 here, and then 5x. These would always get canceled. I would always end up with x. And that is what the reason for that is, because I did u sub at this step, which I shouldn't have. It's correct solution. And in fact, a book would have it this way, but I don't think it's actually sleek, because the other way is better. It kind of showcases that that regardless of what is in the argument of tangent, as long as you write the same argument for secant also, it's the same expression, so that you would do u sub only for this, but not for this part, right? So let me actually solve that and put it in here so that you can just see it and screenshot it. Okay, this is the better solution in my opinion, where you just rewrite it like that, and then you do u sub at this stage, and then you obviously end up with the same answer, right? I think it's cool to see different ways to solve things, because it just teaches you so much. Okay, the final, you made it. I'm so proud of you. You're such a dedicated calculus student. You're going to places. Okay, so this is the last trick number 7, Pythagorean conjugate. And what are, without the Pythagorean, normal conjugates? So this one is a part of a conjugate pair, one of the pairs. So if you had A minus B, you write the same thing but with the opposite sign, and then you gave it its pair, and together they are in love forever, and you can put them together as difference of squares, and that's just beautiful. And remember, I showed you for the trick number 6, this very fundamental relationship, which is Pythagorean theorem. Cosine square x plus sine square x is 1. That's super important. And the Pythagorean conjugates come from that idea. That anytime you have, if instead of 1 plus sine x there, if I had 1 minus sine square x, oh, that would be great, because then I could go that equals to cosine square. But I don't. I have sine x and also plus and no squares. And by the way, the whole problem with this integral is that I can't take this right now. If you say that this equals to u, you can never say that, because unless you have derivative of this sitting here, that's not a good option, and you don't, because derivative of sine is cosine. So that's not here. Okay, so I'm going to multiply it by Pythagorean conjugate, which is this expression, 1 plus sine x with an opposite sign in between, which is minus. And this whole fraction equals to 1, correct? So that's why I'm able to do it. You can multiply anything by 1 without upsetting anyone. Dx. Now I'm going to multiply it through. Here I have 1 plus sine x, 1 minus sine x. That is difference of squares. That is 1 square minus sine square x. And in the denominator, I have 1 minus sine x dx. Okay, feeling much better because the denominator equals to cosine square x. And the denominator, I still have 1 minus sine x, and that's fine. Now I'm going to do trick number 2, separate the numerator, which we learned in this video already. Do you see how extremely versatile and powerful that trick is? We already used it 3 times. This is the third. I have integral of 1 over cosine square. What is 1 over cosine? That's secant, right? And what is 1 over cosine square? It's secant square, right? And what is integral of secant square? What is the derivative of tangent? Secant square x. Am I getting ahead of myself? Probably, but I'm getting quite excited. So this one we solved because this is secant x, secant square x. But this one is interesting. Okay, follow this logic. You have sine x over cosine square x. Well, sine x over cosine square x, it's sine x over cosine times cosine, because that's what square is. It's two of them, right? 2 cosines in the denominator. So what you have is sine x over cosine x times 1, right? Over cosine x. Well, you write this separate, that sine over cosine, that's tangent x. 1 over cosine, we already said that, it's secant x. Okay, so instead of this, you write, well, first of all, let's handle that. That is secant square x dx minus tangent x secant x dx. Notice that I have reminded you your distant past calculus 1 derivatives. Derivative of secant x is tangent x secant x. Antiderivative of tangent x secant x is secant x, because when you're taking integral, what question you're asking is, whose derivative is this? That's the solution to that integral. By the way, it's also part of, both of these integrals are part of your basic rules of integration. But if you want to remember them from Calc 1, then the derivatives are here. Oh, okay, so I'm taking these integrals already in the first one and the second one. There you go. You made it, you did it, you're done. These are the 7 steps. Pythagorean conjugate it's an interesting and very important. I have a video. This is my very favorite, special, dear to my heart integral. And this one gets solved using Pythagorean conjugate. There's another way to solve it, but one of the more kind of intuitive way to solve it is Pythagorean conjugate. So this is a very versatile trick that you can now have in your toolkit and apply to many, many integrals. So hopefully these 7 tricks will make your life much easier, and so that you can enjoy Calculus 2, because when you have these types of powerful tricks, then math is very fun and enjoyable. Thank you so much for watching.